Thank you for the opportunity to speak at such a respectable forum. Our talk is Emergence of a vortex structure in the boundary layer during the transition to turbulence. We present the results by our team at the Hydrobionics and Boundary Layer Control Department of the Institute of Hydromechanics, National Academy of Science of Ukraine. We share the importance of the questions raised about vortices. A vortex is not such a separate element introduced from the outside, but an integral part of a flow, arising when the flow itself changes due to various dynamic or thermal factors. The relations between the parameters of the resulting vortex structures and dynamic or thermal factors is a subject of study in hydro and aeromechanics. This talk presents the results of numerical simulation of the emergence of vortex structures in the boundary layer on a plate and in the initial section of a pipe at transitional Reynolds numbers. In the first case, the laminar turbulent transition processes are studied on a locally deformable surface. It is such a flow control method inspired by dolphins, which are capable of dampening and redistributing boundary layer disturbances due to viscoelastic properties of their skin and peculiarities of their movement. Also, the processes of transition from laminar to turbulent flow in smooth pipes is considered. This process is often encountered during the startup phases of heat exchangers. We found a number of common features in these two different problems as to the emergence of vortex structures in the boundary layer during the transition to turbulence. We consider three-dimensional problems of incompressible fluid flows on a flat plate, locally disturbed by forced regular surface oscillations according to a given analytical law, and a flow in a pipe with possibility of changing the dynamic viscosity coefficient in a non-isothermal medium. The classical system of unsteady three-dimensional Navier-Stokes and continuity equations for incompressible viscous medium is considered. For a pipe flow, additional energy equation is considered with the dynamic viscosity coefficient described by the following polynomial, taking into account the non-isothermal formulation of the problem for considered temperature range. The boundary conditions are no slip for velocity components at fixed walls, initial velocity profile specified at the inlet, and the outflow at the outlet. It is Neumann boundary condition with zero gradient for all flow variables. A certain area of a plate located at some distance downstream from the inlet is actively perturbed in the form of a traveling wave, where A, lambda, and Cf are the amplitude, length, and phase speed respectively. Direct numerical simulation of the problem is carried out by finite volume method with total number of computational cells up to 3.5 million. For numerical simulation of the flow on a deformable surface, we use dynamic mesh techniques, which allow automatically unsteady rebuilding the computational mesh during runtime in accordance with an unsteady change in geometry of the deformable area. First, we consider the fluid flow on a flat plate locally disturbed by forced regular surface oscillations in the form of a traveling wave. Here you see the classical results of the plane linear stability theory, the so-called neutral stability curve, which shows the dependence of the dimensionless wave number on the Reynolds number defined by the momentum loss thickness. This neutral stability and the growth curves are obtained analytically and numerically as solutions of the Orzo-Merferti problem in the class of traveling waves, derived from the linearized Navier-Stokes equations for small amplitude waves. The region within the neutral curve corresponds to the conditions for stability loss in a laminar boundary layer. Therefore, we set the task of studying the nonlinear response or receptivity of a laminar boundary layer to forced local surface oscillations in the form of a traveling wave. The main parameters of this traveling wave are the amplitude, wavelength, and the phase speed. Based on the neutral stability curve, we select the study parameters. Specifically, in this study, we consider long wavelength disturbances with dimensionless values of 5 and 7.5, and a phase speed in the range from 0 to 0.5 of free stream velocity, which are clearly located both within and outside the neutral curve. Here are the experimental results on emergence and development of three-dimensional vortex perturbations during the laminar turbulent transition process. The main transitional three-dimensional structure is a lime-shaped or so-called hairpin composite vortex. This vortex goes through a number of unsteady transformations, including closing a pair of longitudinal vortices onto the head part, separation of the head from the surface, formation of near-wall low-pressure zone, fluid ejection from the outer region, and finally occurrence of turbulent bursts phenomenon. Numerical simulation is capable of reproducing the vortex evolution in the laminar turbulent transition, and it is demonstrated in a typical flow pattern below. In the present study, we excite natural boundary layer disturbances by imposing local forced surface oscillations and examine how change in values of the traveling wave parameters affects the flow vortex structure. Here you see the unsteady visualization of the boundary layer vortex structure locally disturbed by surface oscillations in the form of a traveling wave. This is visualization of either surfaces of the parameter q, which is the second invariant of the velocity gradient tensor, and a vortex is defined as a flow region where q is positive. It is where the rotation dominates over the viscous shear. The traveling wave generates transverse vortices in the wave troughs, which are then transformed downstream into lambda-shaped structures consisting of longitudinal vortices closed onto the head part. The next stage is destruction of the lambda structure and the span-wise extension of the disturbed zone. In the side view, it's clearly seen that the head part of the lambda structure separates and rises to the boundary layer outer region, gradually destroyed as moving downstream. Despite the primary planar structure of the initiating traveling wave, the boundary layer doesn't preserve downstream the respective planar structure and is necessarily transformed into a system of three-dimensional multi-scale vortex structures with a mostly longitudinal orientation. This slide shows the effect of the front wide of the generated traveling wave at different phase speeds and wave amplitudes. With a narrow front, which is analogous to the three-dimensional perturbation, a clearly defined lambda-shaped structure is generated, which subsequently breaks down into smaller scale structures across virtually the entire computational domain. As the phase speed increases and the traveling wave amplitude decreases, the front wide of the generated wave fundamentally changes the wave vortex pattern. In the planar case, the transition scenario escapes the stage of a large-scale lambda-shaped structure formation, while maintaining the phase speed and amplitude of the initiating traveling wave, but the final stage is essentially independent of the initial perturbations. This slide demonstrates the effect of phase speed on a plane traveling wave with a dimensionless wavelength of 5 at the highest amplitude considered. At zero phase speed, which is equivalent to the flow over a corrugated surface, transversal vortices remain stable in the corrugation troughs, with natural transversal vortices of the boundary layer emerging in the wake. For a non-zero phase speed of the traveling wave on the surface, the transversal vortices lose stability even in the traveling wave zone. Transversal oscillations with a wavelength of the order of the traveling wave appear on the vortex shell. The amplitudes increase and the transversal vortex loses stability. As the generated traveling wavelength increases to 7.5, the stability of the transverse vortex more clearly reflects the change in the phase speed. At low phase speed, the transverse vortex loses stability in the wake of the generated section, and as the phase speed increases, the vortex flow pattern replicates the instability scenario observed at a shorter wavelength. Here you see detailed Q visualization in the flow region with destruction processes of a planar transverse vortex. It is clearly seen that the initial stage of the transverse vortex destruction goes through the appearance of a transversal wave with wavelength of an order of the primary traveling wavelength with a rapidly growing amplitude. This slide shows the fundamental difference in the formation of the velocity and vorticity field in the central longitudinal cross-section over a corrugated wavy surface and over a surface unsteady deformable in the form of a traveling wave for different phase speeds. The flow structure over the deformable section of the surface is gradually transformed as the phase speed increases, from formation of stagnation zones in the wave troughs up to intensive transverse large-scale vortex structures. This slide demonstrates the receptivity factor or reaction of the boundary layer on the surface perturbations in the form of a traveling wave. The first three ones demonstrates the effect of changing the phase speed at a high wave amplitude, and the last two show the effect of decrease in wave amplitude at a constant phase speed. All the cases show different vortex structures in the wake, but there is a number of common features in all the figures. The common feature is the transition of a transverse vortex formed in the traveling wave troughs into a three-dimensional lambda-shaped vortex structure with its subsequent selective transformation to chaos or a practically deterministic state. From the next slides, one can study in details the boundary layer vortex structure for different traveling wave parameters. Here are cubicalization at top, angle, and side views, as well in the center and the periphery longitudinal cross sections, and a detailed enlarged floor fragment. For the case of the highest traveling wave amplitude, the boundary layer is the most disturbed and span-wise extended when developing downstream. In the enlarged picture, we see, along with the main lambda structure formed in the center and gradually destroyed downstream, a set of smaller scale lambda structures formed and developed in the periphery region. In general, we see a complex multiscale three-dimensional vortex structure of the boundary layer becoming more and more chaotic downstream. At lower traveling wave phase speed, there is less intensive growth of the boundary layer disturbances downstream. The multiscale lambda structures are mostly concentrated around the central flow region, and there is a weak span-wise extension of the wake downstream. At the lowest traveling wave phase speed considered, the lambda structures are fully concentrated in the central region, and there is no span-wise extension of the wake downstream. There is also no separation of the lambda structure head part, which doesn't rise to the boundary layer outer region and destroy as for the higher phase speeds. The next slides show changes in the flow vortex structure with decrease in the traveling wave amplitude at a fixed phase speed. There are the analogous tendencies of the boundary layer structure with increase in the traveling wave amplitude, as in the case of increase in the phase speed. The multi-scale lambda structures are mostly concentrated around the central flow region, with a weak span-wise extension of the wake downstream. At the lowest traveling wave amplitude considered, the boundary layer disturbances are fully concentrated in the central region, and there is no span-wise extension of the wake downstream. This slide shows change in drag on a locally deformable surface for the corresponding parameters of the traveling wave. It is obvious that a change in the flow vortex structure leads to the corresponding changes in the viscous drag on the surface. On the deformable surface, there are zones with drag reduction, and the greater the traveling wave amplitude and phase speed, the clearer the drag reduction zones, where the transverse vortex maintains its shape and intensity. From the moment of formation and during the collapse of lambda structures, there are only streaky zones of increased drag compared to that of a conventional boundary layer at the same Reynolds number. A stripped structure of the drag reduction on the surface evidences the fact that the boundary layer doesn't preserve the primary planar structure of the initiating traveling wave and is necessarily transformed into a system of three-dimensional multiscale vortex structures with a mostly longitudinal orientation. Here are patterns of the drag distributions on a locally deformable surface for different phase speeds of the traveling wave for the corresponding case of planar traveling wave on the surface. For a zero phase speed of the traveling wave, either for a stationary rough surface, there is almost no drag perturbations on the surface in the wake flow. With increase in the phase speed, there is a distortion of the transverse strips, which reflect the emergence of transversal instability waves, and in the wake flow region, the drag distributions on the surface take a stripped structure with a mostly longitudinal orientation. The next slides show a flow vortex structure formation in a pipe for non-isothermal flow. The processes of emergence and development of the boundary layer perturbations on a smooth flat surface and at the beginning of smooth pipes has much in common, provided that the thickness of the boundary layer formed on the pipe surface remains smaller compared to the pipe radius. Therefore, the process of transition from laminar to turbulent flow regime in a pipe can be conditionally divided into transition stages. Stage 1, oscillation initiation. Stage 2, development of regular axisymmetric pressure and vorticity waves, which almost completely correspond to the linear stability theory of emergence of disturbances and their development. Stage 3, development of a deterministic pressure wave and vorticity with torus shape. Stage 4, destruction of the deterministic vortex structure. At the inlet of the pipe, as the leading edge of the plate, the flow contains the entire frequency spectrum of the boundary layer's natural disturbances, and taking into account their small magnitude, high frequency disturbances quickly decay, as shown by the cubicalization, but low frequency disturbances remain in the boundary layer. Their propagation downstream is recorded at the corresponding Reynolds number in the form of discrete traveling waves with a certain length and phase speed. The longitudinal sections of the formed toroidal vortex structures have an ellipsoidal shape with a rather large ratio of the axis lengths. Increasing the Reynolds number affects the dimensions of the ellipses. The width, lambda, and the amplitude A of the corrugations decrease with increasing Reynolds number. The vortex structure becomes smaller. There is a shift in the point of origin of toroidal vortex structures closer to the inlet of the pipe with increasing Reynolds number. When reaching the regime of developed turbulence, the change in the position of the initial formation of toroidal vorticity becomes less noticeable. Cubicalization of the vortex structure in the pipe for isothermal flow and in the case when the inlet temperature is greater than the wall temperature and vice versa, showed a significant influence of the viscosity gradient on the shape and scale of the vortex structures and the stability loss by the flow and the transition process itself. Thus, toroidal structures are observed only in the case of a negative viscosity gradient in the near wall zone. In the case of a positive viscosity gradient or isothermal formulation of the problem, the transition occurs without zones 2 and 3. The structures formed during the transition are small scale. If analyzing the spectral characteristics obtained on the basis of the pressure and drag values, then the following trends can be seen in zone 3. With increasing Reynolds number, the signal power increases, and one significant frequency is distinguished. At the same time, the significant frequency gradually increases from 2 Hz to almost 5 Hz with increasing Reynolds number. At the end of the pipe, in the zone of chaotic disturbances, the spectra show a tendency to expand into the region of higher frequencies. The difference in spectral power, although remaining significant, becomes smaller in absolute values as compared to the inlet section of the pipe. When the flow is non-isothermal, a thermal boundary layer is formed on the pipe walls, which leads to a corresponding significant change in the dynamic viscosity coefficient. Thus, in water, when the temperature changes by 30 degrees, the dynamic viscosity coefficient changes twice. In the considered temperature range, at a negative viscosity gradient in the near-wall zone, the steady-state velocity profile differs significantly from the parabolic one by the presence of an inflection point and a small thickness. And vice versa, we obtain a more field velocity profile at a positive viscosity gradient. Therefore, while maintaining the flow rate, the cold wall slows down the flow near the wall, but accelerates the flow core, thus increasing the required pressure gradient. This is a demonstrative slide which shows difference in the quality of Q and Liutex vortex visualizations of the problem of fluid flow generated by a pair of dimples. In contrast to the Q visualization, Liutex method represents vortex structures more clearly, with designating the vortex rotation signs. So the Liutex vortex flow visualization method shows great promise, and we are currently working on applying this method to the problems outlined in this talk. And finally, conclusions. Based on direct numerical simulation of emergence and formation of a vortex flow structure in a laminar boundary layer on a flat surface and in the initial section of axisymmetric pipe, one can make the following conclusions. Emergence of wave disturbances in both the external flow on a plate and the internal flow in a pipe occurs identically and corresponds to the linear criterion of convective stability of a laminar boundary layer. Transformation of the first plane mode plate and the first axisymmetric mode pipe of the vorticity wave into a transversal and toroidal vortex, respectively, occurs according to the same scenario, with the dimensions and the convective stability time decreasing with an increase in Reynolds number. The formation and destruction of the transversal and toroidal vortices occurs in a similar manner, with the formation of transversal and azimuthal oscillations on their surfaces, an increase in their amplitude, and the subsequent formation of lambda-shaped structures at the vortex antinodes. With increase of Reynolds number, the analogy between the vortex structure of the near-wall layer on the plate and in the pipe is broken, with the helical mode with the same vorticity wavelength appearing in the pipe. Traveling wave initiation on the surface leads to development of a vortex structure downstream, which shows significant dependence of convective stability of the transverse vortex formed in the traveling wave troughs on the transverse width and amplitude of the traveling wave in the range of wavelengths and phase speeds considered. It is impossible to preserve a deterministic vortex structure in the non-separated near-wall flow region. In order to create a quasi-stable vortex structure, vortex initiators distributed over the surface are necessary. For this study, vortex flow visualization based on the Liutex method is highly promising. Thank you for your attention.